Right. Let's see.
All right. So first, just some basics about the exam itself. So it is available in the testing center until next Wednesday, which is the 25th, I believe. So it is like a Wednesday to Wednesday availability, which is a little bit different. This test does take quite a bit longer than previous exams to take, so I do recommend giving yourself a little bit of extra time in the testing center to make sure that you can complete it on time. There's only 16 questions, so there's not a lot of questions. It's just that with all these bigger formulas that we have in this unit, the questions just take a longer time to work through. So there's going to be 9 multiple choice questions, and my slide says Unit 3 and Unit 4. They're predominantly from Unit 3 and Unit 4, but really there could be anything even all the way back to, you know, the first chapters that we covered, so Units 1 and 2 as well. So there's not really like calculations from any of the previous chapters or units or anything, but definitely the concepts. So I recommend just going through the test review sheets from all the previous tests and looking at that the first page that has all the concept terms on it, and just going through and just making sure you remember all those different things, because a lot of those terms, they're probably still familiar and you're like, oh yeah, but then if you sit down and think, oh, do I really know what this means? You might have forgotten some things. You know, like back in chapter 3, when we talked about things like density curves and z-scores and percentiles, and even though we kind of throw those terms around a lot still now, like just thinking about what those definitions are would be a good thing. And then definitely all the stuff that we had last unit, all those newer concepts like p-values and confidence intervals, and you know, what does the confidence level mean, and how do we come up with a confidence interval, and what is the sampling distribution, like central limit theorem, law of large numbers, like all those kind of concepts would be good to go over as well. So after the multiple choice, there's 7 problems. In that 7 problems, there's 5 of the 4-step method problems. These are going to be very similar to the last 2 pages of the test number 3, the last exam, where basically on the top part of the page, you're going to do the test of significance, and then at the bottom of the page, you're going to do the confidence interval for the same data. And then after those 4-step problems, then there's 2 sample size problems where you just have to calculate what sample size you would need for a desired margin of error. So I'm saying allow at least, you know, 2.5 hours, and you kind of know what kind of test taker you are to know exactly how long to allow. And a really great idea would be to treat the review sheet. There's 5 problems on the review sheet on the 2nd page of the review. And if you kind of treat that like a pre-test and just sit down and work through all those problems, if you add about 20 minutes to the time it took you to do those problems, that's about how long the exam will take. So, and here's this is that review sheet for test 4. And really all I'm trying to point out with this is just that there wasn't a lot of new concepts in this unit. And in fact, I really had to kind of reach to find anything to put on the review sheet on the front side for concepts, because the concepts aren't new. We've just gotten more complicated formulas, some different scenarios that we've been applying the same concepts to. So the 5 different methods that we've covered in this unit are the one sample t-test for means, the matched pairs t-test, and really the matched pairs t-test is really just the one sample t procedures on the differences. And then we've also done the 2 sample t-test for means, the 1 sample z-test for proportions, and the 2 sample z-test for proportions. So we have 5 different methods that we've looked at. And as I mentioned previously, there's going to be 5 different 5-step problems. There's going to be 1 of each type of problem. So kind of the test taking strategy that I would recommend is, you know, after you finish the multiple choice or whatever, read through all the 5 different scenarios and decide which method goes with which scenario. And just like write it across the top. Because once you've mapped out what you're going to do, then it's really not that hard to work through. Then it's just, you know, kind of just grunt work, just working your way through the problems. But that way you don't start working along and then all of a sudden you're like, oh wait, you know, I feel like I need to use the 2 sample T and I've already used the 2 sample T. So somewhere along the line, then I must have made a mistake somewhere or something like that. So I recommend just kind of mapping everything out and then working your way through the problems. And that kind of helps with process of elimination if you know that there's exactly one of each of the different kinds of problems. So how do you figure out which method to use? Because in the homework, you know, in chapter 20, we learned about the 1 sample T, and then all the homework was about 1 sample T. And then in chapter 21, we learned about the 2 sample T, and pretty much all the homework was the 2 sample T. And on the exam, I'm not going to come out and tell you, as I mentioned, what kind of method you're going to use. You're going to have to decide which method is the right one for you to use. So this is kind of the thought process that I go through when I'm trying to figure out which method is the right one. So the very first thing that I ask is the variable that we're measuring, is it categorical or quantitative? So if it's quantitative, then that means that we're dealing with means. So, you know, some keywords in the problem might be if they're giving you means and standard deviations, X bars, things like that, then you're dealing with quantitative data. Now, if you're dealing with categorical data, then that means that you're working with proportions. So in the problem itself, you're going to be given counts. There's not going to be any means or standard deviations. They might use the word proportion or percentage several times. So those are some kind of key things to look at. And I sent out this flow chart in the email announcement that I sent out yesterday. I think it was yesterday that I sent it out. So basically this goes along with the thought process that I use to decide what type of analysis to do, and then this kind of gives you all the details of everything too. So it's 2 pages, the flow chart. So this page is for quantitative. So if you decide that you have a quantitative variable, then the next thing you need to ask is, well, am I looking at 1 group or 2 groups? And for right now, you can ignore the 3 or more groups because that's coming up in the next unit. So we don't have that for this test. So once you decide 1 group or 2 groups, if it's 1 group, then you know you're doing the 1 sample T procedures. And if it's 2 groups, then you have to decide between the dependent matched pairs situation or the independent 2 sample T procedures. And those 2 right there are the trickiest to tell apart. So here's some kind of things you can look at to kind of tell the difference there. So first of all, look at how the data was collected. So something is considered dependent or matched pairs if knowing something about who is in group A tells you something about who's in group B. So if you think about like a taste test, in a taste test situation, each person would taste both samples, but in a random order. And in that case, if I know who's in the Bluebell ice cream group, then that would tell me exactly who's in the Dreyer's ice cream group because it would be the same people. So that would mean that those 2 samples are dependent or is a matched pairs kind of situation. When you have a matched pair situation, you would have to, well, first of all, you do the randomization within the pair. So if you look at how the randomization was done in a matched pairs, it's going to be within the pair. Also, you have to have the same number of people in both groups. So there's the same number of observations for Bluebell as there would be for Dreyer's. So if it's matched pairs, it has to be the same number in each group. Having the same number in each group is not like a determinant, because if they're independent, you could also have the same number in each group. But if you have a different number in each group, then it is determinant because it means it can't be matched pairs. It has to be independent. So 2 sample. So some other things to think about are, especially as far as the exam goes, are I'm going to give you all the information that you need to do the problem. So for example, I'm going to have to give you any means or standard deviations that you would need to do the problem. So in a matched pair situation, the right analysis would be to do to find the differences and then calculate the mean and standard deviation of the differences. So on the exam, I'm going to have to give you the mean and standard deviation of the differences. Now, if it's a 2 sample independent, there are no differences. So I can't even try to trick you because there's nothing that I could give you because there are no differences in a 2 sample T situation. So I can try and trick you if it's matched pairs, because I could give you the mean and standard deviation of the differences, but also try, give you the, say, the mean of Bluebell and, the mean of Dryers, and then also the mean of the differences. So I could give you extra information in a matched pair situation to try to throw you off, but I wouldn't be able to do that in an independent two-sample situation. So basically what I'm saying about that is, on the exam, if I'm giving you the mean and standard deviation of the differences, that's a very good indication that we're talking about a matched pairs kind of situation. All right, so on the other side, if we decide that we have a categorical response variable, then you just have to ask one group or two groups. And once you decide that, then it's easy. You know exactly which type of analysis to use and which formulas and everything. All right, so this is just the stuff that I already just talked about. All right, so we're going to practice. I have some different scenarios here, and we're going to see if we can figure out which type of analysis that we're going to do. So the first thing that, well, here, I'll read the scenario first, then I'll say the first thing. So it says a botanist is developing a strain of tomato plants that is expected to yield larger tomatoes than existing strains. She needs to estimate the weight of the tomatoes produced by the plants of the new strain. She grows a crop of the new strain, randomly selects 100 ripe tomatoes, and measures their weights. What type of confidence interval should she use? Okay, so first thing we want to figure out is, what is it that we're measuring? So in this case, we're measuring the weight of the tomatoes. So is weight categorical or quantitative? Okay, so if you want, up to your little camera, you can give me a C for categorical or a Q for quantitative. All right, perfect. So weight is quantitative. So that means we're dealing with means. So then we have to decide if we have one group or two groups. Any guesses? Yeah, in this case, we just have one group. So she just has like one sample that she took. So she has one sample. We're talking about quantitative variable, so we're dealing with the one sample T procedures. All right, next one. A tax preparation company wanted to compare the quality of the work done at its two offices. 75 returns prepared by each office were selected at random. Of those sampled at the first office, 5 had errors. Of the returns sampled at the other office, only 3 had errors. Is there a difference between the true proportions of erroneous returns at the two offices? Okay, so think about what we're measuring here, and think about, sometimes it helps to think about what is an individual. So in this case, an individual would be a return. So think about what you're measuring on each return, which would basically be whether or not they have errors. So is that categorical or quantitative? Yeah, categorical. So we have a categorical variable, which means we're dealing with proportions. And something else that kind of helps us figure that out is, I don't know where my pen's not working. Okay, is that down here it talks about the true proportions down here. Let's see if my pen's not plugged in right. Hang on. Oh yeah. Oh my gosh. Okay, sorry, just 1 second. Yeah? Yes, you can hear me? Yes, okay. Sorry. Everything was plugged into weird things over here. Please move this window away from the shared application. Okay. All right. So, so it kind of lets us know that we're dealing with proportions because it talks about proportions here in the problem. So then we have to decide if we have one group or two groups that we're comparing. And this case, they talk about two offices here. So we know that we're dealing with two groups. So two groups, categorical data would say two proportions. All right. Can you guys still see everything on the screen the same way? Because it's giving me an error, but I'll just ignore the error. So researchers wanted to estimate the mean difference between an adult's rate of respiration under two conditions: a high level of carbon monoxide in the air and no carbon monoxide in the air. 40 healthy adults were randomly selected to participate in a study. Each adult's rate of respiration was measured twice, once while breathing an air mixture that had no carbon monoxide in it, and once while breathing in an air mixture that had a high level of carbon monoxide in it. Which mixture they breathed first was determined randomly. All right, so looking here, we can see that the response variable is rate of respiration. So is rate of respiration, is that categorical or quantitative? Quantitative, exactly. So are we looking at one group or two groups here? Are we comparing one thing or two things? Two things. So we have the high level and the no carbon monoxide that we're comparing. So then we have to decide if the two groups are dependent, meaning there was matching or pairing, or if they are independent. So I guess that would be like a D or maybe a number 1 for an I. All right, so in this case, we had the same adults that had both treatments, so they breathed both airs. So knowing who's in the high carbon monoxide group would tell you exactly who's in the no carbon monoxide group. So that makes this one a dependent or matched pairs type of design. So we would do the matched pairs, which is really the one sample t-test on the differences. All right, studies have linked the size of the brain in infant humans to the development of disorders such as autism. 12 autistic boys who had brain scans as infants were randomly selected. Then 12 non-autistic boys who had brain scans as infants were also randomly selected. The scans were used to compare the size of the brains of the autistic boys to the size of the brains of the non-autistic boys. All right, so it looks like we are measuring brain size, and I'm guessing that they don't measure brain size in, small, medium, large, extra large. I'm guessing that's some kind of numerical measurement. So if it's some kind of numerical measurement, we're gonna have a quantitative variable. So if we have a quantitative variable, in this case, are we comparing one group or two groups? Two groups, right? We have the autistic boys and the non-autistic boys. So then we have to decide if these two groups are dependent, meaning there's matching or pairing, or knowing something about who's in the autistic group would tell us something about who's in the not autistic group, or we have to decide if they're just independent from each other. Yeah, in this case, they are independent from each other. Whoops, sorry. I keep getting this weird error thing. I'm just gonna see if I can get rid of it. Oh, and maybe it's just gonna hang out there for the whole time. So these are independent because they randomly selected the autistic boys, and then separately they randomly selected the non-autistic boys. So the selection of the sample was separate from each other. So there's no matching or pairing or anything like that. If it was a matched pairs design, they would have to do something like take twins where, one of the twins was autistic and the other one wasn't, or something like that. That would make it matched pairs. But they don't have that in this case. So it's the independent two sample. All right, next one. The Nellie Mae organization reports that the average credit card balance cardholders in the US have is $5,134. A financial planner wants to determine whether the average credit card balance of cardholders from Austin is lower than this. She takes a random sample of 100 credit card holders in Austin and finds that the mean of her sample is 4,578. Is there evidence of a difference? All right, so this time we're measuring credit card balance here. I lost my pen altogether. Okay, so we're measuring credit card balance. Is credit card balance categorical or quantitative? Quantitative. So then are we looking at one group or two groups? Okay, how many samples did we take? We just took one sample. We took one sample of Austin people. So situations like this can be a little bit tricky because you think, well, we're comparing Austin to the US. Doesn't that seem like two groups? But you have to look back at where's the sample coming from. So the whole sample came from Austin. So we took one sample from Austin and we're comparing that to a single number from the US, like some known, number from the US. So in this case, we do just have a one sample. So it's going to be a one sample T procedures. All right, engineers creating a new kind of fabric, select 36 swatches of the fabric and run them through a machine that simulates wear and tear on the fabric. 18 swatches are randomly selected to stay in the machine for 40 minutes. Another 18 are randomly selected to stay in for 50 minutes. Each swatch is given a quality rating from 1 porous condition to 100 perfect condition. Do swatches left in the machine for 50 minutes have a lower quality rating than those left in the machine for 40 minutes? All right, so this time we're measuring quality rating. So is quality rating, is that categorical or quantitative? Ooh, we have a mixture of opinions here. So first of all, is quality rating a number? Yes, right? And would it make sense to talk about the average quality rating? Also, yes. And so in this case, we do have a quantitative variable. So quality rating is quantitative. So now we have to look at, are we comparing one group or two groups? Two, right? So we have the 40 minutes group and we have the 50 minutes group. So we have two groups. So now we have to decide if the two groups are dependent, meaning there was matching or pairing, or if they were independent. So they were just selected separately from each other. All right, so I'm not sure if I can tell everybody's hand signals. So maybe we shouldn't play on the same baseball team or anything. But basically in this case, we have an independent situation. So they had all the swatches that were tumbling around in the machine, and then they stopped the machine after 40 minutes and they randomly selected 18 swatches. So they randomly selected the 18 from everybody to come out, and then they let the rest of them go in for the remaining 10 minutes, and then they compared the two. So because the randomization was just taken, everybody, and we just randomly selected which ones were going to be in which group from everybody, that makes it an independent rather than a dependent. So in order for it to be a dependent in this case, they would have had to maybe take the swatches, wash them, and then maybe cut them in half or something and pull half out and leave half in or something like that. It's the only way I could think of to do a matched pairs in this situation. So the correct answer, though, is independent to sample. All right, medical imaging studies have found a possible link between autism and the absence of two structures in the brain, the superior olives that are used for interpreting facial expressions and other social cues. Doctors want to know whether the link is real. They randomly select patients at risk for autism. Those that have superior olives are placed in one group and those that do not in another. All the patients are screened for autism. The percentages of autistic patients in the two groups are to be compared. Which hypothesis test is most suitable for this comparison? All right, so this one I think can be a little bit tricky because when you start asking, okay, well, who are the individuals and what did we measure on the individuals? Well, in this case, it's almost like we measured two things, right? We measured whether or not they had superior olives, and we also measured whether or not they had autism. So we kind of look at what our purpose was here. And our purpose was to compare the two groups. So it says one group is the superior olive group. So that's one group. And then the other group is going to be the do not have superior olives. So that one was kind of like our grouping variable. And then after that, then they screened them to find out whether or not they had autism. So whether or not you have autism, that's going to be a categorical kind of variable. So we have a categorical variable, and we have, as we just described, we have two groups, the superior olive group and the no superior olive group. So if we have two groups, categorical variable, then that leads us to two proportions. All right, a medical researcher studies a strain of E. coli to see how resistant it is to antibiotics. She prepares 50 cultures of the strain and subjects them all to a common antibiotic. After 48 hours, she classifies each culture as either viable or non-viable. She wants to estimate the true percentage of viable cultures. What type of confidence interval would be best for her to use? All right, so in this case, it looks like we're measuring viable or non-viable. So is that going to be categorical or quantitative? Exactly, categorical. So we have categorical variable. Do we have one group or two groups? One, just one. So she just took 50 cultures of the same strain of E. coli. So it's all one sample. And another clue that we're just talking about one is it says we're looking at the true percentage. So that would indicate just one percentage that we're looking at here. So if we have categorical and one group, then we just use the one proportion, Z procedures for one proportion. All right, an Olympic swim coach would like to know if a new type of swimwear will help his swimmers swim faster. He randomly selects 8 swimmers and has each of them swim the 100-meter freestyle, once in the new type of swimwear and once in their usual swimwear, with the order being determined at random. He wants to estimate the true mean difference in each swimmer's times. A confidence interval for which of the following would be the most appropriate for this study? So in this case, we're measuring the time to swim the 100-meter freestyle. So swim time, that's going to be quantitative, exactly. So we have a quantitative variable, and how many groups are we comparing, 1 or 2? All right, we actually have 2 groups. So we have the new type of swimwear and the usual swimwear. So usual versus new type. So he has each swimmer that swims in both types of the swimwear. So does that make this dependent, meaning matched pairs, or independent? Yeah, this one's dependent because the same swimmer had both treatments. So knowing who was swimming in the new type of swimsuit would tell you exactly who's swimming in the usual type of swimsuit because it's the same swimmers. So this one is a paired situation. So you'd use the paired T, which, as I mentioned, is just really the one sample T procedures on the differences. All right, so moving on, let's talk about sample size for desired margin of error. So there's 2 of these sample size problems on the exam. And the key to these sample size, well, there's a couple keys to these sample size problems. They're not really that hard per se, it's just remembering a few things. So the first thing to remember is make sure you're using the right formula for the right situation. So in the last unit, we talked about sample size as well, but our formula in the last unit was sample size when we were talking about means. And in this unit, we learned how to find sample size when we're dealing with proportions. So you just have to read the problem and make sure if it's asking for sample size in a proportion situation or sample size in a means situation. So looking here at this problem, it says, suppose you want to estimate the proportion of McDonald's patrons who choose diet drinks over full sugar drinks to within plus or minus 4% with 95% confidence. In a small pilot study, 45% of patrons chose diet. What size sample do you need? Okay, so if we look at what we're measuring here, choosing diet drinks, is that going to be categorical or quantitative? Right, categorical. So we're dealing with proportion. So that just means, hey, we need to make sure that we use the sample size formula for proportions. So that sample size formula looks like this. So N is going to be equal to Z star over M, quantity squared, times P star times 1 minus P star. So looking at this current problem right here, we know we're going to need to know how confident we want to be because that's going to help us figure out our Z star. We also need to know M, our desired margin of error, and P star, which is our best guess for P. So starting with confidence level, it says we want to be 95% confident. So we'll put 95%. And if you recall, Z star for 95% confident is 1.96. So, and if you forgot what Z star for 95% confident is, if you look on table C, then you look in the column for how confident you want to be and the row for Z star, and it'll have the 1.96 there. Okay, then we have M, our desired margin of error, and it says that we want to guess this to within plus or minus 4%. Now, one of the keys to doing these sample size problems, right, is that all the percentages, when they go into your formula here, they have to be in decimal form. So 4% as a decimal is 0.04. All right, and then P star, that's going to be your best guess for what P is. So sometimes they're going to give you something to go off of. Like in this case, it says in a small pilot study, 45% of patrons chose diet. So since we have pilot study data, we can use that 0.45 as our P star value. If they don't tell you anything, like you have no clue, then the most conservative P star you can choose is 50%, which is 0.50. So that's what you would use. But if they give you something, use the something, because you'll end up with a smaller sample size. Okay, so now that I have all these numbers here, we can go ahead and plug those in. So I'm going to have N is equal to Z star, which is 1.96, over M, which is 0.04. That quantity squared. And you wouldn't believe how often people forget that little squared sign up there. So just don't be one of those people. So then times P star, which is 0.45, times 1 minus 0.45. All right, so then we can go ahead and start working through this. So if you have your calculators, get them out and work it with me. So I'm going to have 1.96 divided by 0.04, which gives me 49, and then I'm going to square the 49, and that gives me 2401. So for the first little bracket part here, I have 2401. Then I'm going to work on the right side here, so I'm going to have 0.45 times 1 minus 0.45, which is 0.55. So 0.45 times 0.55 gives me 0.2475. All right, then I multiply those together and I end up with 594.2475. So in a sample size situation, when we're trying to figure out what sample size we need, we always, always, always round up. So when I say what size sample do I need? Well, I need 595. I'm always going to round up to the nearest whole number. Take the whole person and not just part of a person. All right, so let's look at the next one here. Suppose you want to estimate the proportion of students at ACC who have been to iFly. You want to be 90% confident and estimate this proportion to within plus or minus 3%. What size sample do you need? So I'll throw up our formula up here again just for reference here. So I'm going to have N is equal to Z star over M squared. And I'm doing the proportion formula again because we're talking about proportions, estimating proportions. All right, so again, I'm going to need how confident I want to be. That's going to help me figure out my Z star. I'll need to know the desired margin of error. And finally, I'll need to have a P star value. So starting with C, my level of confidence says I want to be 90% confident. And Z star for 90% confident is 1.645. So then I have M. M is my desired margin of error. And I want my margin of error to be plus or minus 3%. So written out as a decimal, that's going to be 0.03. Now this problem did not give me any pilot study information or anything else to go off of, so I really have no idea on this proportion. So if I have no idea, then the value to use is 0.50 or 50%. And something to just kind of make note of is that it's 50%, which is 0.5, not 0.05. So a lot of times, because we use alpha of 0.05 a lot, then, they both have 5s and 0s. So it's easy to kind of get confused as to what number you use here. So it's not a 0.05, it's a 50% for the P star value. All right, so now just plugging everything into my formula, I'm going to have 1.645. I feel like I need to, I don't know, get a new driver or something for this computer pen. It's been driving me nuts lately. Keeps drawing random lines everywhere. So 1.645 over m, which is 0.03. That quantity squared times 0.5 times 1 minus 0.5. So starting with the bracket section first, I have 1.645 divided by 0.03. Then I'm going to square that quantity. So after I square it, I get 3006.94444 repeating. No, wait, 694 is what I get. There was 6 in there. 69444 repeating. And then I'm going to have 0.5 times 1 minus 0.5. So that's really just 0.5 times 0.5, which is 0.25. So then I do that multiplication there, the 3006 times the 0.25, which gives me 751.67. And of course, this is a sample size problem. We always round up for sample size problems. So I would actually need to sample 752 people for that one. All right, moving on. So this next section, I have several, like 5 four-step method problems. And we're not going to have time to go through all of them. So I think I'm just going to pick the hardest 2, the ones with the yuckiest formulas, and talk through those. And then I'm working on making videos of the other ones. So if you want to watch how to do any of the other ones, you can do that. I've made one of the videos so far, but I still got 2 more to make. Because these problems take forever, especially if you've done the chapter 23 homework. Like, it's kind of a beast, those formulas. So, so this first one here, a study was conducted on adults age 18 and up. One question they were asked was, are you a morning person or an evening person? Here's the results for 2 age groups, 18 to 29 and 30 to 49. Is there evidence of a difference in the percentage of morning people for the younger versus the older age group? So here's the data. And, if we're thinking about this on an exam, which type of method would we use here? Well, what are we measuring here? Well, we wanted to know whether or not people were morning people or evening people. So that's going to be categorical. And we're comparing 2 groups for that categorical variable. So we're dealing with 2 proportions. All right, so step 1 is going to be state. So we just want to know, is there a difference in the proportion of morning people for the younger versus the older age group? So step number 2 is plan. First thing we do under the plan step is we identify our population parameters. So we have 2 population parameters because we had 2 groups that we're comparing here. So P1 would be the proportion of younger morning people, and then P2 would be the proportion of older morning people. Now, the fact that I assigned P1 to be younger and P2 to be older, that was arbitrary. We could switch that around. I could have made P1 older and P2 younger, and you would end up with the exact same results. So basically the main difference is that we would get like in one way we're going to get a positive test statistic, and the other way we're going to get a negative one. But because we're always looking for the tail value when we're finding our p-value, then either way we're going to end up with the exact same p-value. So you don't have to worry about which one you need to call which, because you'll end up with the same answer either way. All right, so back to my plan step here. Once we've identified the population parameters, next thing is to write the hypotheses. So we have null hypothesis and alternative hypothesis. Under the null hypothesis, we're saying it doesn't make any difference how old you are. There's the same proportion of morning people. So in other words, P1 equals P2. So, back when we learned about writing hypotheses, we said the equal sign always goes in the null hypothesis, and that still holds for these proportion problems. So equals is always going to go in the null hypothesis. So our alternative hypothesis, that's going to be based off of what our practical question says. And we just wanted to know, is there a difference in the proportion of morning people for younger versus older? So a difference, that's kind of code word for not equals to. So for our alternative hypothesis, we'll have P1 not equal to P2. Okay, so now we've got our hypotheses. Just one thing I wanted to point out about the hypotheses, because this is just somewhere where I typically see people make mistakes, is that when we're talking about proportions, it gets a little bit tricky because there's so many times that we use the letter P. So we have P, and then we have P hat, and now we have P1 and P2 and P hat 1 and P hat 2, and we've had P star. And there's just all these different P's, and they all look similar. So it's not like when we were talking about means and we had X bar and mu, which look quite a bit different from each other. Now we have P and P hat, which seem very similar. So one thing to watch out for is that when you write your hypotheses, they always need to be about the parameters, and the parameters don't wear hats. So just remember that there are no hats in the hypotheses ever. You should never have hats in the hypotheses. So I get a lot of errors on the test where people put P hat 1 equals P hat 2, but there's no headwear. Okay, so looking at the important information that I need to gather, we have these two samples here. So we have the younger group, the younger and the older. So in the young group, we're looking at the, dumb pen, we're looking at the number of successes and also the sample size, and then we'll end up calculating our P hat 1 as well. And the way that the data was given in this particular problem, it wasn't quite as straightforward. I'm going to be a little bit more straightforward on the exam. So they did tell the number of successes, which is the morning people here. So that's 97. But they didn't give us the sample size. Instead, they just basically gave us the morning and evening person. So we just have to add those two numbers together to get the sample size. So I'm going to take 97 plus 131, which gives me 228. So my total is 228. All right, and then if I calculate that P hat 1, that's just going to be 97 divided by 228. 97 divided by 228, which is 0.4254. And when you're finding your initial P hat here, then you can go ahead and round to 4 decimal places here. Don't round any more than 4. You can start with 4 decimal places right here, and then as you're working through the problem, try not to round as much as possible. And then when you get to the end again, you can round to 4 again. Okay, for the older age group, we're also going to need the number of successes, the sample size, and we're going to calculate P hat 2. So for the number of successes on this one, we've got 177. For my sample size, I'm going to have to add 177 plus 167, which gives me 344. So N2 is 344. And then for my P hat 2, then I just take that 177 divided by 344, which gives me 0.5145. All right, now we're almost ready to go on to the next step, except that for the test of significance for proportions, then we need something called the pooled proportion, or the pooled P hat. And I'm going to write it up here because I'm running out of room down there at the bottom. But this P hat, which is the pooled proportion, looks at, let's see, proportion. Okay. The pooled proportion looks at, basically it's saying if the null hypothesis was true, if P1 was really equal to P2, then there's no reason to go around talking about everybody separately. Instead, let's just throw everybody together, you know, one big happy family. If young and old are all the same, then we don't need to go around saying this percent of young people are morning people and this percent of old people are morning people. Instead, we could just say this percentage of everybody are morning people. So, so that's what this pooled proportion says. It says, okay, if the null hypothesis is true, let's just throw everybody together. So you look at the total number of successes in both samples combined, divided by the total number of observations in both samples combined. So in this case, we're going to have 97 plus 177 in the numerator, and then 228 plus 344 in the denominator. So order of operations says we got to do the addition first. So add in the numerator, then add in the denominator, then divide. So I'm going to take 97 plus 177, which is 274. And then I'm going to take 228 plus 344, which is 572. And I'm going to do the division now, divide those out, and I get 0.4790. Okay, so that's my pooled proportion that I'm going to use in the formula when I finally get to the part where I can actually do the test statistic on this problem. And since I'm going to move to another slide, I'm just writing down these numbers because I should have put them on the other slides ahead of time, but I didn't, so I should have. So I'm just writing them down so I have them. So I have 0.5145. All right, so one thing to keep in mind about this pooled proportion, just like where I see some errors sometimes in calculating it, are the pooled proportion is still a proportion. And proportions should be numbers that are between 0 and 1. So if you get a pooled proportion that is more than 1, then you did something wrong. So like sometimes I see people that just add P1 and P2 together, or that do the order of operations wrong and end up with some funky number or something like that. So if you get a number that's bigger than 1, you know, you've made an error somewhere. Also, the pooled proportion should be somewhere between P hat 1 and P hat 2. So it's not going to be directly in the middle unless your sample sizes are exactly the same, because it's kind of a weighted average. It's not a real average, not a direct average of those two numbers, but it should be somewhere in between those two numbers. So those are some like error check things you can use. Okay, so next we can move on to step 3, which is the solve step. And the first thing we do in the solve step is check our conditions. And we have basically 3 conditions here. First condition is that we have 2 simple random samples. So looking at my question here, it just says that a study was conducted. It doesn't necessarily say how they did the study, but it doesn't give us any indication that they did anything bad or that they, you know, just took a voluntary response sample or anything. So we always give them the benefit of the doubt unless we can prove otherwise. So we're going to say check on the 2 simple random samples. The large populations, we just need the population to be at least 10 times bigger than the sample. And if we look back here at our sample sizes, the younger people, there was 228. So if the population, we need the population to be at least 2,280. And we're talking about young people. So are there at least, you know, 2,280 young people out there? Oh yeah, easily. Same thing with this 30 to 49-year-olds. You know, are there at least 3,440 30 to 49-year-olds in America? Yes. So this is a condition, and we should check it, but this one's an easy one to meet because typically we have huge populations and we're just taking a little sample from them. So it's not usually an issue. Okay, then we have the condition of a large enough N. And that we have a rule of thumb for this. And the rule of thumb says that all 4 of these quantities have to be at least 5 for the test of significance and at least 10 for the confidence interval. So we want n1 times p hat 1, n1 times 1 minus p hat 1, n2 times p hat 2, and n2 times 1 minus p hat 2. We need all of those things have to be at least 5. So I wrote down all my numbers from the other page. So N1 was 228. So we have 228 times P hat 1, which was 0.4254. Whoops. Multiply those together, then I get 97. Then I have 228 times 1 minus 0.4254. And that's going to give me 131. Then I have N2, which is 344, times P hat 2, which is 0.5145, which gives me 177. Oops, forgot to put the parentheses on that one. Then I have 344 times 1 minus 0.5145, which gives me 167. All right, so I look at all these numbers and I say, you know, are they bigger than 5? And yes, clearly they're all bigger than 5. So we do meet that condition. Another way to look at these numbers here for the 2 sample case is these are all just successes and failures in the individual sample. And that's actually what we got right here in our table, the way that they gave us our data. They gave us the top row here is the successes and the bottom row here is the failures. So if you know how to find those, you don't actually have to work out this math this way because it's the same numbers as those. All right, so we finally got done checking all the conditions. We're ready to get to the meat of the problem, which is where we calculate the test statistic. So we're looking at a 2 sample Z statistic for proportions. And that looks like this. So we're going to have P hat 1 minus P hat 2 divided by square root of P hat times 1 minus P hat times 1 over N1 plus 1 over N2. All right, so now we can just plug in everything that we know here. So P hat 1 was 0.4254 minus P hat 2, which is 0.5145, divided by square root of that pooled P hat that we looked at, that we calculated on the other page. So that was that 0.4790 times 1 minus 0.4790 times 1 over N1, so that's 1 over 228, plus 1 over N2, which is 344, so 1 over 344. All right, now we just got to work through the math here. So I'm going to start with the numerator there. So I take 0.4254 minus 0.5145, and I get negative 0.0891. Okay, now for my denominator, I'm going to do this in parts so that we have some intermediate calculations thrown up here in case you're doing it along with me. So I'm going to start with this first part, the 0.4790 times 1 minus 0.4790. 0.4790. So multiply those and I get 0.249559. 0.249559. All right, now I have this other part over here, the 1 over 228 and the 1 over 344. So I can't remember if I wrote down this trick in the chapter notes file or not. Did I talk about the 1 over x button in the chapter notes? Does that sound familiar? No. Okay, so there's this really cool button on your calculator that's really helpful for doing this part of the equation here. So if you look on your calculator, there should be a button that says 1 over x, or sometimes it says x to the negative 1, or it could even say 1 over n or n to the negative 1 on there. And sometimes it's in the second, like the little things that are above the buttons. I don't know if I can show you mine on here. My calculator is kind of weird though, so. Nope, I don't think it wants to focus that close. There's mine. Did you guys find it on yours? Yes, okay, so here's what you do. So this just makes it so you have to write less things down and everything. It makes it a little bit easier. So for this particular one here, what you're gonna do is you're gonna do 228, and then you're gonna press that 1 over x button, and then you're gonna hit plus, and then you're gonna type in 344, and then hit the 1 over x button, and then you're gonna hit equals. So try that out. And what you should get is 0.0072929416 4165, depending on how many decimal places you're going out. All right, did you guys get the same thing I got? Isn't that the coolest button ever on your calculator? It's gonna save you so much time. Well, at least maybe like, I don't know, a whole minute or something, but trust me, by the end of this exam, you're gonna be happy for every extra minute that you get. Okay, so now that I have those two numbers, I'm gonna multiply those two numbers together and take the square root. So I'm multiplying those two numbers, and I'm gonna take the square root of those. And of course, you know, my general rule for rounding, like if you have to write something down and then type it back into your calculator, my general rule is to use at least 4 non-leading 0 numbers. So, so for this 007 number, don't start counting the 4 until you get to the 7, and then use at least 4 decimal places after that. So if you use that rule, you tend to be pretty safe. Okay, so after I multiplied and took the square root for my denominator, I got 0.042666168. Okay, then I'm going to divide top and bottom here. And I get negative 2.09. Okay, so this is my test statistic. Okay, so here's my test statistic, and this problem, the test statistic is a z, so we're going to use table A to help us find the p-value. So to use table A, first thing I do is go to table A, and I'm going to look up the value of my test statistic. So my test statistic, negative 2.09. Okay, so here's my table. I'm looking for negative 2.0, and then I'm looking at the 09 column down here. So the value for my table is going to be 0.0183. So here I'm going to write that down, 0.0183. All right, once I have the value from table A, then I have to ask, well, is this a tail area? And I know if it's a tail area by how big it is. If it's smaller than half, then it's a tail area, and if it's bigger than half, then it's not a tail area. So in this case, it's much smaller than half, so this is already the tail area. So that's what I want. I want the tail area. If it's not a tail area, I have to subtract from 1. So it's not really supposed to be crossed out, so I'll write it again. Okay, so if it's not already a tail area, then you have to subtract from 1 to get the tail area. Once you have the tail area, you look back at the, where did it go? It's in there somewhere. There it is. The hypotheses, and look at the alternative hypothesis. If it's greater than or less than, it's one-sided. If it's not equals to, it's two-sided. So we have a two-sided test here. And in a two-sided test, the p-value is twice or double the tail area. So p-value equals 2 times the tail area. So in this case, that's going to be 2 times 0.0183. Which ends up being 0.0366. So that's my p-value. Now, the p-value tells you how much evidence you have against the null hypothesis. The smaller your p-value, the greater the evidence that you have. So typically, we don't have an alpha value on this one. So if we don't have an alpha, we usually use 0.05 as our alpha. And in this case, our p-value would then be lower than alpha. And when p is low, HO must go. So we're going to reject the null hypothesis and conclude that there is a difference in the proportion of morning people for the younger versus the older age group. I think I have it written out here. So we reject H0. We have sufficient evidence that there is a difference in the proportion of morning people for younger versus the older age groups. And we can even take it one step further. If you don't on the exam, it's okay. If you just stopped, right here, that's fine. But looking at the data that we collected, we're able to tell what direction that difference is. So based on our sample data, we can tell that older people have a higher proportion of morning persons than the younger people. And we can tell that just by looking at our sample proportions, because the older people had a higher proportion than the younger people. All right, so the next question would be, well, how much is that difference? And if we want to know what is the difference in the proportion of morning people for younger versus older age groups, then the appropriate analysis would be a confidence interval. So the next step would be to construct the confidence interval for this data. So just like on the last exam, that's what you're going to do on the exam. So the confidence interval formula looks like this. So we have p hat 1 minus p hat 2 plus and minus z star times, and this one was it. This one was the yuckiest formula of the whole semester, I think. So square root of p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 over n2. All right, so notice that the standard error that we use here is different than the standard error that we used when we did the test of significance. So in the confidence interval, we're not going to use that pooled proportion that we used back when we did the test of significance. So they're different. When we have proportions, the two formulas have slight differences in them. So you just have to watch for that. Okay, so plugging in everything that I know here, I'm going to have 0.4254 minus 0.5145 plus and minus z star, and we're making this up as we go along. So let's just say that we're, let's be 95% confident. So z star for 95% confident is 1.96. So I'm going to put in 1.96 here, times the square root of 0.4254 times 1 minus 0.4254 divided by n1, which was 228, plus we have p hat 2, which was 0.5145 times 1 minus 0.5145, silly thing, divided by 344. All right, so now we're just going to work through the math here. So I get 0.4254 minus 0.5145. That gives me, that part's the same as the previous problem, negative 0.0891 plus and minus 1.96 times square root. So I'm going to do each of these little portions separately under here just for some intermediate answers. So I get 0.4254 times 1 minus 0.254, which is 0.2443484. I divide that by 228, and I get 0.0010720826 plus, and I'm going to do the other portion here, so I have 0.5145 times 1 minus 0.5145 divided by 344, and I get 0.000726132299. All right, so now I'm going to add those together and square root them. When I do that, then I end up with 0.04240537. Okay, now I'm going to multiply that by 1.96. And I get negative 0.0891. So finally I get my margin of error, which is 0.0831. So to calculate my confidence interval, I'm going to take negative 0.0891 minus 0.0831, which is negative 0.1722. Then separately, I'm going to take negative 0.0891 plus 0.0831, which gives me negative 0.006. All right, oops, I didn't mean to cross that out. So there's my confidence interval. So I'm still going to state my sentence about my confidence interval. So we'd say we are 95% confident that the difference in the proportion of morning people for younger versus older ages is between negative 0.1722 and negative 0.006. All right, and again, it didn't really matter which one I called p hat 1 and p hat 2. The way that I did it here with the younger people being p hat 1, I got negative numbers. That just means that there was somewhere between 17 and 0.6% fewer morning people in the younger age group. If I would have flip-flopped those, I would have gotten positive numbers, and that just means that there would be somewhere between 0.6 and 17% more morning people in the older group. So it's just two ways of saying the exact same thing. So it's all good. All right, finally made it through that problem. So my recommendation is find the nasty 2-sample proportion problem on the test and do that one first and just get it done, because after you finish that one, then everything else is going to feel like super easy. And then, I don't know, maybe then you'll be less hating me by the end of the test, because by the last ones you'll be like, oh, these 1-sample T problems, they're a breeze. Okay, so I am going to skip ahead to, not this one, but I do have a video of this one that I'll post if you want to watch how to do this one. The only thing I want to point out on this one here is, well, I think this one just has the conclusion on it. But this one was a taste test between General Mills and Target versions of Lucky Charms. So taste test is going to be a matched pairs type of situation. And of course, in a matched pairs, then the appropriate analysis is a 1-sample T procedure on the differences. So notice though, in this case here, and possibly on the exam, I'm not going to say for sure one way or the other, but that I gave you all kinds of information, but all you really need is the differences column, and the rest of the stuff here is just there to throw you off and confuse you. So in a matched pair situation, all you need are the mean and standard deviation of the differences and nothing else. So, okay, no, we're not gonna do that one right now either. Let's skip to the other hardest one, which is this one here. So this one says a randomized clinical trial of 135 youth aged 10 to 17 years diagnosed with chronic migraine were assigned to one of two treatments: cognitive behavior therapy, CBT, or headache education classes. Both groups also received medication. 20 weeks after treatment, the severity of migraines for each subject was assessed using the Pediatric Migraine Disability Assessment Score, the PEDMIDAS. The 64 people in the CBT group had a mean of 15.5 and a standard deviation of 17.4. The 71 people in the education group had a mean of 29.6 and a standard deviation of 42.2. Is there evidence of a difference in the treatment methods? So this one here, we're measuring these scores on the PEDMIDAS, so that's going to be quantitative. And we're comparing two different groups here. We're looking, or two different treatments, basically, this cognitive behavior therapy one and the headache education. So we have two groups. And in this case, the two groups are independent because it's different people that were assigned to these different groups. So they took all 135 youth and they randomly assigned them to be in one of these two treatments. So that means we have the independent two sample T procedures that we're going to do for this one. Okay, so first step is state the practical question. So when we're stating our practical question, there's different ways of stating it, and sometimes it gives it to you in the problem. Like, it would actually be fine if you wanted to just use this that they give you here in the problem as the state part. When I write my state statements, I like to make it reflect what the alternative hypothesis is going to be, because if I can kind of formulate that in my mind and write it out, then I feel like it's much easier to figure out everything else. So if I do that, then I would say, is there a difference in the PEDMIDAS scores for the the CBT versus the headache education group? So if you do it that way, then usually this starts with an is here. So under the plan step, the first thing we do is identify our population parameters. So in this case, we have two because we are dealing with two means. So we're dealing with means. So our population parameters mu1 and mu2. So mu1 would be the mean PEDMIDAS for the cognitive behavior 1, CBT. And mu2 would be the mean PEDMIDAS for the headache education. We'll call that HE. So then we're going to go ahead and write our hypotheses. So our hypotheses are null hypothesis. Under the null hypothesis, we're saying, hey, there's no difference between these two treatments, so mu1 equals mu2. And under the alternative hypothesis, in this case, we wanted to know, is there evidence of a difference? So once again, difference, keyword for not equals. So we have mu1 not equals to mu2. And then we just need to gather the important information. So we have the CBT group and we have the headache education group. For both of these, we're going to need to know the mean, standard deviation, and sample size. So the mean for the headache education had a mean of 15.5, I'm getting that from up here, and a standard deviation of 17.4 right here. And it said there was 64 people in that group, so that's N1. For the headache education, this is going to be X bar 2, S2, and N2. X bar 2 says there's a mean of 29.6, standard deviation of 42.2, and N of, where is it, 71. All right, so I've gathered everything that I need. I'm ready to move on to step number 2, or step number 3 actually, which is the solve step. So under the solve step, first thing we do is check our conditions. So first condition is that we have 2 simple random samples. So back here says that it was a randomized clinical trial of the youth that had this migraine issue. So we do meet the randomization requirement, 2 simple random samples. Next, we want both populations to be normal. And they didn't give us the data, so we can't do a stem plot or anything to figure it out. But our rule of thumb says that if we add the sample sizes together, so if I add 64 and 71, and it's more than 40, then it doesn't really matter what our population shape was, we're good. So clearly if I add 64 and 71 together, that's going to be more than 40 because they're individually more than 40. So we're okay to proceed based on that. And then the samples being independent, that just says, hey, did we choose the right method? Because this is the independent 2-sample method that we're trying out here. And yes, those 2 samples were independent. They took the kids and they randomly assigned them to the 2 groups. There was no matching or pairing. Looking in this case, you can see that we have a different sample size in each group, which is another indication that we have independent samples, because if it was matched pairs, it would have to be the same number in each group. All right, so next we're ready to calculate the test statistic. So this test statistic is a t-test statistic, and t is equal to x bar 1 minus x bar 2 divided by square root of s1 squared over n1 plus s2 squared over n2. So looking at my numbers over there, I can plug everything in that I know. I have 15.5 minus 29.6 divided by square root of 17.4 squared over 64 plus 42.2 squared over 71. All right, so now I'm going to start working on the math. So I start with the numerator. So I have 15.5 minus 29.6, which is negative 14.1, divided by square root of, and I'll do these 2 calculations separately, so I have some intermediate calculation numbers here for you. So I have 17.4 squared, which is 302.76. Then I divide that by 64, and I get 4.730625. It's kind of nice working with not proportions. Then we get a little bit bigger numbers that come out of things. Okay, and then the next side, the 42.2, I square that, which makes it 1,780.84, and then I divide that by 71, and I get 25.08225. So 25.08225. Okay, so now I'm going to add those 2 numbers together and take the square root. And when I do that, I get 5.460117. And then I'm going to do that division, and I get negative 2.582, I guess. Go to 3 decimals, sounds like a good idea. So this is my test statistic. Okay, when we're dealing with means in this unit, then the appropriate table to use to help us find our p-value is going to be table C. Okay, and in order to use table C, there's an extra piece of information that we need to know, and that is the degrees of freedom. So for the 2-sample case, the degrees of freedom are going to be the smaller of n1 minus 1 and n2 minus 1. So in this case, that's going to be the smaller of 64 minus 1 and 71 minus 1. So whichever one's smaller, 63 or 70. So 63 is obviously smaller. So we're going to end up with 63 degrees of freedom. So then I would head over to, so basically I'm going to take the degrees of freedom over to table C, and then I'm going to look for my test statistic here. So I'm going to need to know the test statistic. I'm going to need to know the degrees of freedom, and also backing up here, the type of test that I have. So I had a two-sided test because it says not equals 2 there. So my test statistic again was negative 2.582. On table C, I look for the absolute value of that test statistic. Also, notice on this table that there is no 63, so we round down to on degrees of freedom. So rounding down, I get to 60. I'm looking along this row to see where the absolute value of my test statistic, so 2.58, where that would fall between. And it looks like it would be between these two numbers here. Whoops, didn't mean to cross that out. We get 2.39 and 2.660. So this is a two-sided test, so I take that down to my two-sided values down here. And my p-value then is between these two numbers, between 0.01 and 0.02. So p-value is between 0.01 and 0.02. All right, and if the p-value is between 0.01 and 0.02, then that's going to be low. And when p is low, HO must go. So we reject the null hypothesis. I'll back up to show you what that looks like again. Okay, we're going to reject the null hypothesis, and we're going to conclude that the mean pedmitis for the CBT is different from the mean pedmitis for the headache education group. And I don't know which one is better, like a higher score or a lower score, but based on that, we can tell that you get a higher pedmitis score if you take the headache education classes. So conclusion, we reject H0. We have sufficient evidence that youth who receive the headache therapy score higher on the pedmitis than youth who receive the cognitive behavior therapy. All right, so then of course the next question is, how much higher do they score? And that's what a confidence interval would answer. So we'll look at the confidence interval, and then we'll call it a day, because then we'll have looked at the hardest situation for both proportions and means. And I know it's getting late. Whoops, I don't know why I have that there, but okay, we'll look at this here. Okay, so the confidence interval here is going to be x bar 1 minus x bar 2 plus and minus t star, because we're dealing with means, times that standard error. And unlike the proportions, the standard error is the same in both the confidence interval and the test of significance for when we're dealing with means here. So I have the square root of S1 squared over N1 plus S2 squared over N2. So the good news about that is you could actually just reuse the number that you just found. It could save you a little bit of time. The bad news about that is if you reuse the number and you did it wrong the first time, then that means you get it wrong the second time too, which is not happy. So just be careful if you do that. All right, now I've actually, maybe that's why I had this slide here, so I could have all my numbers here. So my numbers are, in fact, maybe I'll do it on this page. Okay, so my x bar 1, I'm going to have 15.5 minus 29.6 plus and minus t star. Now, t star is based on the number of degrees of freedom and how confident we want to be. So let's stick with 95% confident, how much I've been feeling today. Okay, and we already said previously that degrees of freedom was equal to 63. So I'm going to go back to table C here. I'm going to look for 95% confident, and I didn't have 63, but I'm going to use the row for 60 degrees of freedom. I'm going to see where those two intersect, and it looks like, wow, that really turned out to be 2.000. That's pretty cool. Okay, so 2.000 is going to be my T star. Okay, and then it's going to be multiplied by S1, which is 17.4 squared over 64 plus 42.2 squared over 71. So working through these calculations, and since some of these are really similar to calculations that we just did, I'm not going to put as many intermediate steps up there as I had before. So I get negative 14.1 plus and minus 2 times, and like I said, this is actually this same number here that came from the denominator over here. So 5.460117. So 5.460117. So that would make my margin of error let's see, let me do the calculation, then I'll write down the margin of error. Better sequence of events there. I get 10.92. So if I have negative 14.1 minus 10.92, then I get negative 25.02. And if I have negative 14.02 plus 10.92, then I have negative 3.1. So that would be my confidence interval. So we are 95% confident that the difference in mean head-MIDAS scores for the CBT versus headache education treatments is between negative 25.02 and negative 3.1. And the negative just indicates, again, that the headache education has a higher score than the cognitive behavior therapy score. Whew. All right, okay, made it to the end of both of the two toughest type of problems on there. The one sample problems are a breeze compared to these, well, I think. One thing I just do want to point out about these means problems, like one of the most common errors that I see all the time on these is forgetting to use T star here. So for some reason, you know, you're doing the test significance at the top of the page, and then you're doing the confidence interval at the bottom. And for some reason, at the top of the page, when you're finding your p-values, everybody's like, oh yeah, I got to use table C. And they do everything great. And then they get to the confidence interval part, and all that stuff goes out the window, and everybody just wants to use Z star. And part of it's because like you've memorized like the 3 major Z star values that we have. So it's almost like automatic, like you see the star and you're like ready to write things out. But just remind yourself or put a note on your cheat sheet or something that when you're doing the confidence interval for anything dealing with means, so that's going to be 3 different problems on this test, the 1 sample T, the matched pairs, and the 2 sample T, that you have to use T star, which is going to involve the degrees of freedom and the confidence level. And if you remind yourself of that, then you should be pretty good. So does anybody have any questions about anything? All right, you can see that these problems, they just take forever. So I know the test kind of does take forever. There wasn't really any way to get around that just with all the material that we have here. So I'm sorry in advance, and you know, feel free to, I don't know, throw darts at my picture or something when you're done taking the exam, and then we can go back to being friends the day after. All right, well, I will hang out for a few more minutes if anybody else has any other questions, or definitely feel free to, let's see, stop.